Have you ever wondered how complex instructions given to a machine, like move arm left, translate into precise physical actions? Robots interpret direct programming commands through a layered process, starting with high-level code written by a human programmer, which is then systematically broken down and executed by the robot's control system as fundamental machine operations. At its core, this interpretation relies on a hierarchy of software and hardware. Programmers typically use specialized robot programming languages or general-purpose languages like Python or C++ to define tasks. These high-level commands, such as defining a path or gripping an object, are then processed by a compiler or interpreter, which translates them into a lower-level, machine-readable format. This intermediate could often interact with the robot's operating system, or a framework like the robot operating system, which manages resource allocation and orchestrates communication between different hardware components and software modules. The control system then utilizes mathematical models, including forward and inverse kinematics, to convert abstract spatial commands into specific joint angle trajectories and motor commands. For a programmer, this means writing code that leverages the robot's application programming interface, or a PI, to specify desired states or actions. For example, a command to move a robotic arm to a specific three-dimensional coordinate is not just a single instruction. It requires the API to calculate the necessary joint angles for each of the arm segments, considering its physical constraints and current position. These calculations are then translated into voltage or current signals that drive the robot's motors, precisely controlling their speed and position. Understanding this chain of command allows engineers to debug and optimize robot behaviors more effectively. A key concept here is the distinction between task-level programming and motion-level programming. Task-level commands describe what the robot should achieve, like pick up the red block, while motion-level commands specify how it should move, detailing joint velocities or end effector trajectories. The robot's internal software bridges this gap, decomposing tasks into executable motions, often leveraging sophisticated motion planning algorithms that account for obstacles and dynamic environments. This multi-layered abstraction is fundamental to developing intelligent and adaptive robotic systems. Ultimately, a robot's ability to interpret direct commands stems from its well-engineered architecture, allowing abstract human intentions to be transformed into precise physical movements, making complex robotic operations both predictable and repeatable.
If you love robotics, like, subscribe, and keep building with us.